In this video, we're going to look at sigma notation, the tool that we use to represent sums, and we're going to see some of the ways that we can manipulate expressions involving sums to write them in equivalent but perhaps simpler forms. So let me remind you about what sigma notation is first of all. When we're describing a sum, you can describe it using this Greek letter sigma, and we include some sort of limits which tell us where do we start and where do we end. And we have some expression that we're adding up, which in this case, when we're talking about series, usually that's going to represent the terms in some sequence. All right, so let's define some of these quantities. So 0 represents the lower limit, or the starting value for the sum. The number written above the sigma is the upper limit, or the ending value. The variable denotes what's called the index. That's the thing that changes from one term to the next. And so k is going to cycle through all the values from 0 to n, all the integer values, that is. So k will go through 0, 1, 2, 3, all the way on up to n. And then the thing inside is what's called the term. And so this sum represents a 0 plus a 1 plus, and we'll continue on until we reach a n. So the sigma notation is just a shorthand for the sum on the right-hand side. But what we're going to find is that it's much easier to work with sigma notation, especially when you're adding up an infinite number of things, which is what we're usually interested in with series. And we're also going to see that sometimes you can recognize patterns more clearly when you know how to manipulate sigma notation. So let's look at an example. Here's a sum. The sum of 1 over n, or 1 over k rather. We'll use k for our term, our index. And k is going to go from 1 to 10. And notice that represents the following quantity. When I plug in k equals 1, I get 1 over 1, which is just 1, plus the next term in this sum would be for k equals 2. And so we'll have a 1 over 2 in the denominator. And well, then 1 over 3, and so on, until I get to the last value, which was a 10 in the denominator. All right, so instead of just writing out all of the fractions, 1 over 1, 1 over 2, 1 over 3, and adding them up all the way up to 1 over 10, I can write this much more concise representation here on the left. However, there are other ways to represent that exact same sum. So for example, notice that if I were to write the sum from k equals 0 to 9 of 1 over k plus 1, that would give me exactly the same thing. Here the index starts with 0 and it ends at 9, which means there are a total of 10 terms that we're adding up. So we have the same number of terms as the sum above. But if you actually plug in k, you'll notice we'll have, well, when we plug in k equals 0, it'll be 1 over 1, which is 1. And then when you plug in k equals 1, we'll have 1 over 1 plus 1, which is 1 over 2. And the denominator will just increase by 1 each time, finally ending with 1 over 9 plus 1, which is 1/10. So it's a different looking formula, but it represents the exact same thing. And of course, we could continue to adjust this. We could take the sum from k equals 2 to 11 of 1 over k minus 1, and that would give us the exact same thing. All right, so the way we write a sum using sigma notation is not unique. There are many ways to describe the same sum, and so once in a while you'll find it's useful to be able to switch in between those different representations. All right, so how do we do that? Well, really there's a couple of steps. How do we shift the limits? Well, the first step is we need to adjust both the lower and the upper limits. And the thing to keep in mind there is that we want to keep the same number of terms. Right? So if we're adding up from k equals 1 to 10, and we want to start with 0, that means we can't go all the way out to 10 anymore. We have to stop at 9, so we include the same number of terms. Once we've adjusted our limits, the next step is going to be to replace the index inside the sum. And ultimately what that's going to mean is we're going to be replacing something like k, k is going to be replaced with k plus 1 or k minus 1. And that's going to depend on exactly which direction you're shifting the limit. But again, the hope is that you will be shifting it consistently so that your sum will go through exactly the same terms. Okay, so let's do an example now. Let's look at the following sum, the sum of k minus 1 all over k squared minus 2k plus 2 from k equals 1 to 100. And let's see if we can write that with k starting with 0. Okay? So following the guidelines laid out above, the first thing we'll do is we'll rewrite the sum with a new value of k at the bottom. K equals 0. Now, because we've decreased the starting value by 1, we'll probably need to decrease the ending value by 1 as well to keep the same number of terms. In the original sum, we had 100 terms we added up. Now we need to have 100 as well, and so we'll go from 0 to 99. Okay. Now, everywhere that we had a k in the original sum, now we will have decreased it by 1 because we've shifted our index, right? So before, when I plugged in k equals 1, now if I plug in k equals 0, I will have decreased that by 1 unit. So what that means is we need to counteract that change if we want to represent the same sum. So since we decreased the range by 1, we are now going to replace all of the k's with something that is 1 larger than k to sort of undo that. All right, so what I'm going to do is I'm going to copy the same expression inside the sum, the same term, but I'm going to replace every single k that I see with a k plus 1, and I'm going to use parentheses to make sure that we distribute things properly. So on the top, we had a k minus 1, and so that's now going to become a k plus 1 minus 1. On the bottom, we had a k squared, so that's now a k plus 1 squared. And on the bottom, we also had a 2k, that's now a 2k plus 1. And then, of course, we have the 2, but 2 doesn't have any k's in it, so shifting my index does not affect that in the least. And if you check, so let's just look at the first term. On top, what happens when we plug in k equals 1? We have 1 minus 1 over 1 squared minus 2 times 1 plus 2. And on the bottom, the first value was k equals 0. And so plugging that in, we will have, notice, 0 plus 1 minus 1 over 0 plus 1 squared minus 2, 0 plus 1 plus 2. And you can easily check that those are indeed the same. Okay, so that's good news. It seems like our sums are equivalent. But the better news is that if we now simplify the terms, we actually can come up with a nice formula for this sum that's more convenient to work with than the one that we started with. So let's FOIL this out. On top, we had, we'll fill in our sigma notation first of all. We had k plus 1 minus 1, so notice that's just a k once we cancel out the ones. And on bottom, if we FOIL that out, we'll have from k plus 1 squared, that's k squared plus 2k plus 1, minus we had 2 times k plus 1 plus 2. And if you multiply or start doing some cancellation now, you're going to notice that things simplify down quite nicely because we have a 2k and a minus 2k, as well as we're going to have a negative 2 and a plus 2. And so we're left with just k squared plus 1 in the denominator. Okay, so we can rewrite our limits of our sum as well as the terms of our sum so that the index starts at a different value, but the resulting terms that we add up are exactly the same. And we could do the same thing. Suppose we wanted to start with k equals 2. So the original was the sum of k minus 1 over k squared minus 2k plus 1 from k equals 1 to 100. Say I wanted to start with 2. Well, if I want to keep 100 terms, I can't stop at 100. I need to go one further now, right? And then if you look at the terms inside, where I plug in a 1 in the original, I'm now going to have a 2, which is too big. So I'm going to need to replace k with k minus 1 if I want the first term and each of them to match. So my new sum would be k minus 1 over k minus 1 squared minus 2 times k minus 1 plus 1. In this case, it doesn't simplify down quite so nicely, but these sums are indeed equivalent. All right, so on some of the WebWork problems, you may find that you have a formula you would like to use, and it looks an awful lot like what you have in the problem, except it starts with a different index. And based on what we've just seen, what we now know how to do is shift the index so that those formulas that we're going to learn about over the next couple of classes can actually be applied more generally. All right, we will stop there and look at some more examples in the next video.